In today's session of Bridge Course class, we learn an important topic of physics, that is work, power and energy. The objectives of this topic is to understand the concept of work in terms of the product of a force and displacement in the direction of the force. The second objective of this topic is to developing the concept of energy, what it is, how it is transformed and transferred. How is work defined in science? To understand this term, we shall first consider the case when the force is acting in the direction of displacement. Let a constant force F act on an object. Let the object be displaced through a distance s in the direction through of the force. Let W be the work done. Then we define work to be equal to the product of the force and displacement. That is, work is equals to force multiply with displacement, where force is denoted as F and displacement is denoted as S. Then W is equals to F multiply with S. Work is done only when a constant force applied on an object causes the object to move in the same direction as the force applied. Force without motion. In the first figure, you can observe when a force is exerted on an object which does not move. In that case, you can say that no work is done on the object. In the second figure, you can also observe when an object is carried at constant velocity by a force which act at right angle to the motion. In that case also, no work is done on the object. So when is the work done? You do work anytime you exert a force on an object that causes the object to move in the same direction as the force. In addition to this, the force you exert must be in the same direction as the object motion. In the first figure, you can see the work is done on the dustbin because force and motion are in the same direction. As you can see in the figure, force and motion are described with the arrow mark. That arrow mark is acting upward. In the second figure of when is work done, no work is done on the dustbin because force and motion are in different direction. Example for the work done: force exerted by a man on the wall does not do any work. A person pushing on a wall does no work because the wall does not move. Work is done if the object you push moves a distance in the direction towards which you are pushing. Work is said to be done only when a force acts on an object and displaces it or makes it move. The necessary condition for the work done are: a force should act on an object, this is the first condition, and the object must be displaced from its position. If any one of the above condition does not exist, then you can say that work is not done. The example for the no work done is when a force is applied but there is no displacement. Work is said to be done when a force applied on a ball and it moves then you can say that work is done on the ball by the batsman. Thus, work done by a force acting on an object is equal to the magnitude of the force, that is F, multiplied by the displacement, that is denoted as S or D, moved in the direction of the force. Work has only magnitude and no direction. So mathematically you can write it as work is equals to force multiplied with distance or displacement, that is W is equals to F multiplied with D. Here the SI unit of work is where force is measured in Newton, where distance or displacement is measured in meter. Then the SI unit of work becomes Newton meter, or we can write it as Joule. Here the unit of work is Newton meter or Joule. Let's take one problem on work. How much work is done by a force of 10 Newton in moving an object through a distance of 1 meter in the direction of the force? Here in this problem, force is given to us, that is 10 Newton, and distance is given to us, that is 1 meter. With these two given data, we have to calculate the work done. Now we have to apply a simple formula of work done, that is force multiplied with distance. When you substitute the value of force, that is 10, multiply with distance 1, then you get 10 joule. So we can say that work done is 10 joule. What is energy? Life is impossible without energy. The demand for energy is ever increasing. Where do we get energy from? The answer is the sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. The word energy is very often used in our daily life, but in science we give it a definite and precise meaning. Scientists define energy as the ability to do a work, energy which makes things happen. The energy in sunlight makes plants grow. The energy in food enables us to move and helps us to keep warm. And the energy in fuel powers engine. The unit of energy is the same as that of work, that is joule. Sometimes a larger unit of energy called kilojoule is also used, that is 1 kilojoule is equals to 1000 joule. Luckily, the world we live in provides energy in many different forms. The various forms include the mechanical energy, that is the sum of the potential energy plus kinetic energy. Along with mechanical energy, we got heat energy, chemical energy, electrical energy and light energy. But here we take only two energy, that is kinetic energy and potential energy. How much energy is possessed by a moving body by virtue of its motion? The kinetic energy of a body is defined as the energy of a body due to its motion. So these are the various examples for the kinetic energy. In nature, the body which moves is having a kinetic energy. The formula for the kinetic energy is, that is K is equals to half mv square. This equation shows that the more mass a body has or the faster it is moving, it means that the more kinetic energy it is got. The second energy is the potential energy. The potential energy of a body due to its position or deformed shape, that is configuration. In physics, potential energy is the energy held by an object because of its position relative to other objects. You can also define potential energy as the energy that is stored and waiting to be used later. The higher the ball, the greater the potential energy. Or you can take the second example for the potential energy is, the more the bow is pulled back, the greater the potential energy. The potential energy of an object at a height, that is the gravitational potential energy. An object increases its energy when the object raised through a certain height. This is because work is done on it against gravity while it is being raised. The energy present in such an object is the gravitational potential energy. The gravitational potential energy is the energy which is stored in an object due to its position above the Earth's surface. And the gravitational potential energy formula becomes mgh, where m is the mass of the body, where g is the acceleration due to gravity, that is taken as gravitational field strength, where h is the height. The mechanical energy. It is the sum of the kinetic energy and potential energy of an object. These are the various examples for the mechanical energy. In the mechanical energy, you have to add the kinetic energy along with potential energy, that is half mv square plus mgh. Power in physics. Power measures the speed of work done, that is how fast or slow work is done. Power is both how much work you do and how fast you do it. So power can be defined as, it is the rate at which energy is transferred or the rate at which work is done. That is, P is equals to W by T, where P stands for the power, W stands for the work done, and T stands for the time taken. So you can rewrite the equation for power as power is equals to work divided by time is equals to, where work can be written as force multiplied with the displacement whole divided by time. Then you can rewrite the above equation like this, that is power is equals to force multiplied with displacement divided by time, where displacement divided by time gives us velocity. So replace displacement divided by time with velocity, then your formula becomes power is equals to force multiplied with velocity. The SI unit of power is measured in Joule per second, or we can also take it as watt.